the first thing that I have here, which we went over, I know, but I'm going to just quickly look at a few of these, is just what a trig graph might look like and how we use the coordinates of those points. So on your x-axis, that's your theta axis now, or angle, whatever you name your angle. Often it's theta, sometimes it's x or a or whatever. But that's what that axis is for. It's for the angle, and then the other one is for the ratio of side lengths. So that's just a number, but these ones are angles measured in gradients. And if you look at this graph, which was the first one you had, how much is each division on the theta axis? Pi over 6 is what we said, right? So each of these little marks is pi over 6. So if we want, so that's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, which we can reduce if we're talking about those angles. But let's just pick one point to look at. If I was going to do this one, what would the coordinates of that red dot be? 7 pi over 6 and 1. And that's all you were doing there was labeling the points. But like I said, I'm not going to do all of them because we already talked about these. I'm going to go over to where you're actually graphing a function. So skip past the table of values to where you were graphing y equals sine x. And hopefully it looks something like this. This is what y equals sine x or y equals sine theta looks like. And you kind of have to remember that. It's going to be a lot easier if you have a basic idea of what it looks like, where its maximum is, where its minimum is, where it crosses the y-axis. Those are some good features to know. But we'll talk about these other things as well: amplitude, period, intercepts, domain, and range. But if you couldn't remember what y equals sine theta looks like, what could you do? You could graph it on your calculator, right? So if you're going to graph it on your calculator, it's just like graphing any other graph, except you want to make sure your calculator's in radian mode. And go to y equals. Just type in sine x. You might want to try this right now. And then the other thing you want to do is set it to a trig window, which is zoom 7. So once we have that graph, there are some features that we want to talk about when we talk about sinusoidal functions, which are like sine and cosine graphs. What you'll notice is like it's a wave function. It oscillates up and down, and that's going to keep going forever, doing the same thing, up, down, as you continue to the left and right. It's just going to keep doing the same thing over and over again. One thing that we talk about is amplitude. Amplitude is how tall it is, but actually it's half the distance between the maximum and minimum. So what would you say the amplitude of this one is? 1. I heard somebody say it. Amplitude is 1. It's half the distance between the maximum and minimum. The period is how far you travel on the theta or the x-axis before the graph repeats itself. For this particular graph, the period is 2 pi. If you look at one complete cycle, it's easiest if you can to start from 0 and just see how far to the right do you go before you reach the same point in the cycle again. So if we start here at 0, it's going to go up, down, up, back to the x-axis again. That's one period, 2 pi, because then it's going to do the same thing over again. But it's that one complete cycle. So you could look at it from maximum to maximum. That distance is 2 pi. Or you could look from minimum to minimum. Or sometimes I look at that central axis. So the center to center. And not just center to center here, because this part's not repeating. It has to go back up again. So 2 pi. Intercepts. So you guys already know what intercepts are. Where's the y-intercept? Y-intercept is at y equals 0. How about the x-intercepts? 0, pi, 2 pi. Where will the next one be? 0, pi, 2 pi, 3 pi, 4 pi, negative 2 pi. So the x-intercepts are at every pi. So we could say n pi, every pi. Negative 2 pi, negative 1 pi, 0 pi, which is just 0, 1 pi, 2 pi, 3 pi, 4 pi, and it keeps going. So n pi, if n is an integer. So positive and negative. And you already know what domain is, just for any graph, so it works the same way here. What would you say the domain is for this one? All real numbers, right? So you could do negative infinity to infinity, or you could say it's, well, x such that x is an element of the set of real numbers if we're calling this y equals sine x. If you're calling it y equals sine theta, then those x's would have to be thetas. And the range of this one? Yeah, less than 1 and greater than negative 1. So you could say it as negative 1 to 1, or y such that negative 1 is less than or equal to y is less than or equal to 1. You don't need to. Sometimes you'll see it with y-er at the end. That's fine. Yeah, you can put it there if you want. I usually don't bother. Y equals cosine theta looks like this, or cosine x. I'm going to call this one cosine x. It looks very similar, right, to y equals sine x. Amplitude's the same, it's equal to 1. Period's the same, it's 2 pi. So we're looking from, here I'd probably look from maximum to maximum. Here, all the way over to here, it's 2 pi. I just like to go from 0 if I can. But you may have just graphed this bit of it from here to there, because I think that's what I had in the table of values, but that distance is still 2 pi. The domain is the same. Is the range the same? Oops. Range is the same. Y such that negative 1 less than or equal to y less than or equal to 1. It's between negative 1 and 1. The intercepts are different though. What's the y-intercept for this one? Y is 1. And how about the x-intercepts? Pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. So we're going to say it's pi over 2 plus n pi, yeah, or pi n, where n is an integer, or you could say n is a natural number and then you need plus or minus n pi, whichever way you'd rather do it. So it's basically the same as a sine function. It's just shifted over. The whole thing is shifted. The sine function goes through the origin and has its maximum at pi over 2. So it would look like this. The third function that you graphed was y equals tan x y equals tan x is different than the other two, like very different. And if you graphed it, you may have had trouble even figuring out what the points were doing. This graph here, tan x is the purple lines, right? The green line, dotted lines, those are the asymptotes. So it does look very different because it's sine x divided by cosine x. So it's a rational trig function. So you should see, though, that it's still periodic, it's cyclical, it keeps going, doing the same thing over and over again. Just so in that way it's similar to the others. But it's not continuous like the other ones are. It has all these asymptotes. What would you say is the period of this one? Is it the same, 2 pi, or is it different? You think it's pi? I think you're right. The period for this one is pi. So if you look here at 0, 0, when does it come back to 0, 0 again? Doing the same thing, so kind of increasing through 0, 0. It happens again here at pi. So that's the period. Or you could look at one asymptote to the next. Negative pi over 2 to pi over 2, that's 1 pi. So that's the period. Intercepts. Y-intercept. X-intercepts. Every pi. Oh, how do we say that before? N pi is how we said it before, where n is an integer. Or you could say something like plus or minus n pi, where n is a natural number, if that's what you're used to and that's what you want to say, that's okay. The domain of this is kind of tricky. Can anybody tell me what the domain is, just in words? What would you say? X cannot equal pi over 2, did you say? You can say the domain is x such that x does not equal pi over 2 plus n pi, where n is an integer. Here you might want to say then x is an element of the set of real numbers as well, but I don't have room, so I'm not going to. We're defining the domain here as what x cannot equal instead of what x does equal, which is kind of strange, but that's the way we have to do it. And the range of this one? Anything? Yep. Is that what you said? Yeah. Y such that y is an element of a set of real numbers. Y can be anything. This is going to keep going up forever. Each of these is going to keep going up forever and just getting closer and closer to that asymptote. And the same thing at the bottom. It's going to go down forever and just keep getting closer to the asymptote.